topic is the protect the data of virtual machines with Intel's MKTME on KVM. Firstly, I'm Huang from Intel Corporation, and I'm working on some virtualization new feature support for Intel's hardware platforms. So today this is my agenda. Firstly, I'm going to talk about some background and give some introduction about MKTME, and then I will give some user case about MKTME, and then our enabling plan and status. So, I think in the era of the cloud, I think the data in the virtual machines, I mean the data of the tenant in virtual machines is becoming more and more important. And how can we make them safe? I mean, so we need to make the virtual machines can be trusted. And ideally, that the tenant may not need to trust the service provider at all, but that requires some technology like the SGX. And and it requires a lot of enabling work. So for the other options, we think that the memory encryption technology is the fundamental of protecting users' data. So we think that. We can use encryption technology to make the VM can be trusted during the VM's whole lifetime. So, if the VM can be encrypted during at rest, it means its image is stored encrypted in the repo, and during a long time when it's running, and during in transit, for example, when it's being migrated, and so that we can some kind of trust the virtual machine. And for the encryption technologies at rest and in transit, we already have some technologies. For example, the Qemu already supports the TLS for line migration, and the Qemu also supports to run the encrypted image directly. But the VM's runtime encryption technology requires hardware support. So AMD, they have their own, which is AMD SME SEV, and Intel has MKTME. And actually, before the encryption, there's more. For example, maybe we needed to launch the VM on the trustiness verified host. For example, we have verified the physical machine that can be trusted from the vendors can be trusted, and the whole stack from the BIOS to the operating system to the hard provider, and they are also verified that can be trusted. So. And so in this case, we can the tenant can launch that VM safely. And for the trustness verification, we need to have some hardware-based root of trust and the attesting service to do that. But today's topic is going to focus on the Intel's MKTME. So what is MKTME? So basically, we add a new AES-XTS memory encryption engine into the data path to the external memory bus. So the data, when the data goes to the memory, it will be encrypted automatically, and when it goes to the CPU, it will be decrypted automatically. And since we are using the AES-XTS, and it uses the physical address as a tweak, which means for the same plain text, and if it is in the different physical address, the cipher text in the memory will be different. And the TME is a total memory encryption, which means once turned on, all the memory will be encrypted by some TME's key, which will be generated by CPU during every reboot. And TME can be enabled, disabled by BIOS, and so so it is transparent to the OS and users. And MKTME is based on the TME, so you have to turn on the TME before you can turn on the MKTME. And MKTME actually adds support to use multiple keys, and it's done by using some upper bits of the physical address as key ID. So here is the detail about the key ID. Basically, MKTME repurposes the upper bits of the physical address as a key ID, and for example, we can and so for example, the physical machine, it can support for example, how many key ID bits, and it is reported by the MSR, and and the operating system can get that information. So by using the key ID, it means the physical address bits is reduced, and the different key ID can actually refer to the same physical address. And the key ID 0 is reserved as TME's key. So yeah, and we have new pconfig instructions to program, to program the specific key ID to be associated with some particular key or some particular mode. Okay, so I might forgot this. So architecturally, we are up to support 15 bits of key IDs, and but in the first server inception, we may support probably 6 bits of the key IDs. So we add a new instruction pconfigure to program a particular key ID to be associated with some particular key, and this instruction is per package, which means if you call the pconfigure on particular core, so actually it's per package. So, and pconfigure supports programming one key ID into 4 modes. Basically, the first is to use the CPU-generated random ephemeral key mode. The key will be invisible to the software, although the software can provide some entrophies for both key and tweak, which will be XOR'd by the CPU. And the second one is to use software-provided key, so which means the software can provide the key and the hardware use the key directly. And the third mode is no encryption at all. Remember that with TME, we actually have the encryption with the TME's key, but we can program the key particular key ID to not using encryption at all, which means we will store the plain text in the memory. And the last one is a clear key mode, which means this key ID will effectively use TME's key. And this pconfigure also allows software to specify some crypto algorithms. So you have an MSR to query that how many algorithms that we can support on this platform, and you can specify one particular one when you are doing the pconfigure. But in the first server inception, we only support the AES XTS 128. So we consider the MKTME, the major user case of the MKTME is the memory protection and isolation. So the protection basically means we use some particular key ID to input the VM's memory at a runtime. And the isolation basically means for different virtual machines, we can apply the different key IDs. So the virtual machines can be isolated. And in terms of software enabling, it's quite straightforward. For CPU success, you just set up the key IDs at the at the page tables entries. For example, for the host page tables, you set up the key ID in the host page tables, and for KVM, you set up the the PT as a key ID in the EPT. And MKTME actually also supports the device DMA. So for IMMU, you basically set up the key ID to the IMMU's page table. And for physical DMA, you just apply the key ID to the physical address directly. Since the logic of KTME happens at the memory controller layer, so it can support the DMA as well. So let's do a recap. So this is the highlights of MKTME. Basically, the one advantage is the guest continues to run without modification to the guest. Basically, we can support to encrypt to the guest can be encrypted with either CPU generated key or the software provided key, and the virtual I/O, including the optimizations. For example, vhost kernels can continue to work as long as you can set up the correct key ID. And we also support the pass-through, the direct I/O, and for example, SRV, all those existing technologies will continue to work. And live migration can also be supported, among the platforms that support MKTME. Theoretically, you can migrate one VM, to the other machine without MKTME, but that will lose the memory encryption. And actually, MKTME also supports NVDIMM. So theoretically, we can support the virtual NVDIMM. But there are some tricky issues of supporting the NVDIMM because of the physical address tweak. Because the encryption uses physical address as a tweak, which means for different physical address, even the same plain text will have the the different cipher text. So for the NVDIMM, so basically it requires that during host reboot the NVDIMM configuration you cannot change. You cannot change NVDIMM configuration and the DIMM configuration. Otherwise, if the physical address changes, so after reboot you are not able to get the data back. And actually, if you are going to support the virtual DMA, you have to make sure that for Qemu's virtual NVDIMM, you have to map map to exactly the same physical address of the NVDIMM previously, right? So far, do you have any questions? Okay, so let's go to the user cases. Basically, we define some user cases, and here I'm going to talk about the tools. So the first one is the very basic, the very basic user case. We just launch a VM with the runtime protection of the MKTME by using the CPU generated key. So in this case, the key will be handled by CSK, basically using the CPU generated key, maybe provided some entrophies from the CSP, and the VM image will be provided CSP as well. And the second one is a complicated user case. For example, we can launch the VM with the at rest, encryption protected, and we can launch the VM with the runtime protection as well with MKTME, and the keys can be fully controlled by the tenant, and we can have the host trustness verified by using the attestation service. And additionally, we can also require the VM images integrity to be verified before launching the VM. And a special one is because the key ID is, we treat key ID as some kind of precious resource. So we can support actually the key ID sharing between among the virtual machines. For example, if one tenant is going to launch several virtual machines with the same tenant key, or the tenant does not care what key to use. It just wants to use the CPU generated key. So in this case, we can actually use the key ID sharing to just use one key ID to launch all those VMs. So the first case is quite simple. We just launch the VM with CPU generated key, and the security property is that we can have the VM runtime protection, and we can choose to have or have no at rest and transit protection. And here there's no host trust verification at all. And here is the second user case. You can see that before we launch the VM, actually the tenant can choose to encrypt its VM image by its own key and upload it to the image, the repo. And then it issues the VM launch command to the cloud manager. And the cloud manager can, before the launch of the VM, it can choose to ask whether the node can be trusted by asking the attestation service. So here we needed to ask the computer to generate some report based on the hardware provided the root of trust and send that to as a attestation service to verify. And after the compute node is verified, so that we can launch the VM, and we can also make the VM images integrity verified before launch that VM. And we can even that, because the VM image or the MKTME key is provided by the tenant, so the computer node has to ask the tenant key server to get the key. And during this, we can even ask the computer node to use a TPM, right, to generate a public key private key pair and ask the key server to encrypt the key before releasing that to the computer node. So in this case, the VM will launched with the runtime protection and at rest protection, and if we use TS is line migration, we can support the in-transit protection as well. And the host trustness is verified. The VM's images integrity is verified as well. And the key ID sharing, the basic idea is we make the cloud software to make the decision whether to share or not, because the cloud software has all the knowledge of the virtual machine, whether they came from the same tenant. So the cloud software should maintain some table, for example, which virtual machines are using which key from which tenant, and when a new VM launch request comes, it first can query whether we can reuse some key or key IDs, and then if we can, then it just get that key or key ID and ask Qemu to launch that VM. Otherwise, it can create a new one and ask Qemu to launch. So basically, the cloud software can update this table, when the VM is launched and when the VM is teared down. So the last is our enabling status. So far, any questions? Yeah, so this is overall enabling. So for the normal case, it's actually quite simple. You just have to set up the virtual machine's memory, in both the Qemu hosts the page table and the EPT, so that the reason is that Qemu has to access the guest's memory. For example, for some emulated device, so we have to make sure that the Qemu process itself can access the guest's memory with the correct key ID. So this is done by setting up the same key ID in both EPT and the Qemu's host page table. And for pass-through, we set up the key ID to the MMU, and for virtual and vhost, if the virtual or vhost kernel it requires to read the guest memory directly, it needs to set up the key ID in the, for example, in the key map, so that it can read out the guest memory. And if we are going to DMA directly to the guest's encrypted memory, so we have to add the key ID to the DMA support, either through the MMU or either through the direct DMA. And the line migration actually is it involves the DMA. So basically, we need to support the DMA with the key ID. So a recap is what we needed to do in terms of enabling MKTME. So from host kernel's perspective, there are those components we need to modify. So first is key ID management API, which we are going to use the key retention service, and we will add a new MKTME type key, and it will just return the handle to the user space, but not actual key ID. And the core MMU code needs to be modified, for example, to manipulate the key ID in the VMA and the page table, and set up the key table in the page fault, something like that. And we will have a new system call to apply some user space processes, particular address range, with some with the MKTM's key handle. And we are going to modify the VFR MMU and the DMA to support key ID as well. And the KVM is quite simple, actually. We just need to set up the key ID in the EPT or the shadow page table. And Qemu, it does two things. So first is it receives the key from the cloud software. And the second one, it is applies the key handle to all the guest's memory by calling that a new added system call. So this is our a proposed modification to Qemu. Basically, we add a new MKTME guest object to carry the MKTME handle. This is actually aligned with MD's SEV guest object. And we're going to use the memory encryption, that property of machine property, to indicate the VM is associated with some key ID. This is consistent with the MD's SEV as well, who introduced the memory encryption property, actually. So the reason is we do not see that we have to set up multiple key IDs for one single virtual machine. So currently, we just wanted to reuse this synth. And here is a simple command to launch the VM with a particular key ID. We use a new added object, MKTME guest, and use a handle from the up layers. So if you write a small script, you can firstly use key retention service that a tool, which is a key control tool, to add a new MKTME type key, and just apply that, and and then assign that key handle to the Qemu to launch that VM. So this is our current status. The specification has been published. You can find that on the website. And for the core kernel enabling, we have some patches already in upstream. For example, the future emulation and the pconfig stuff. And some RFCs has already been sent to the community for feedback. For example, the MKTME key type implementation. And other components still working in progress in internal. We have some code that is working, but it's internal only. And for KVM Qemu, we have done some POC to verify it can actually work. And but in terms of sending out the patch to the community, we have to depend on the core kernel parts ready. Yeah, so that's all. Yeah. Any questions?
I just have one question regarding the tenant keys.
I'm sorry?
Tenant keys.
Yeah. So basically, the tenant key will be provided as a tenant. Okay. If I go back to this slide. Yeah, right. So basically, the tenant key will provide its key server, and there's other. I think there's some other ways, but the typical way is the tenant. When the tenant sends a VM launch request to the service provider, and it contains a key server, so that the the cloud software can ask the key server to release the key.
I don't understand how you secure the key, basically. How is it secure so that it goes to the provider? So.
Yeah, I mean, the communication between key server and the compute node can be protected by the TLS, right? And the other thing is that we can ask the compute node to use the TPM to generate some key pair and use that to wrap the key before releasing that key to the computer node.
So the key is wrapped basically.
Yeah, we can choose to wrap that key. Yeah.
What is it wrapped to? Is it wrapped to maybe something to TIS? I don't know.
I mean, the TIS is a TIS can be established between the key server and the computer node, right? So I think basically with the TIS protection, you can actually send the key directly, right? So because the content will be encrypted by the TLS, but Additionally, you can also ask the key computer node to send you a key pair, by generated by the TPM. So which means only this computer node can decrypt that key. So which will be more secure in our thinking.
So can the guest actually know it's being encrypted properly or with its keys and make these things?
No, I think it's transparent to the guest. Because one advantage of MKTME is we don't have to do any modification to the guest. It's because we set up the key ID in the guest memory. So before we copy any data, for example, BIOS image and other images to the VM to the virtual machine's memory, actually we have already set up the key ID. So once the data is copied into that memory, it will be encrypted, and when guest tries to access those kind of memory, it will be decrypted automatically.
So, would there be any same way of providing like MKTME virtualization, like so that like say you could actually know as the guest like, oh, when I'm writing these things out, like it's actually going into this key.
Yeah. So
now everything seems to be controlled by the physical address in EPT as opposed to the guest physical address inside of the guest page. The guest doesn't know.
okay, so you are talking about exposing MKTME to the guest, right?
Well, the thing
Yeah.
that we want is like, oh, the customer wants actually marketing.
I think so. You have to see the value. Actually, applying the key ID to the guest's physical address won't work, because MKTME only happens at the physical address level. So applying to the key ID to guest physical address won't work. You know, right?
The hardware doesn't provide.
Yep.
That isn't not the thing that I asked the question, but it seems like there's a step missing. Like it's because it's perfectly transparent, you guess doesn't know that any of these things can happen.
Yeah.
So, another question, you said virtual I/O works.
Yeah.
How does it work? It's encrypted, how does you see the pages?
Yeah, so basically the Qemu we see all the guest memory, right? Because it has the same key ID in its own host page table, right? So it's just in terms of the memory access. So if
So it's not protected from Qemu. So Qemu cannot.
right, it's not protected from the Qemu because Qemu has to be part of the TCB, yeah.
But Qemu is a process, so at that point, if I have access to the kernel of the host and I have access to all the memory of the VM.
Beg your pardon?
Qemu is just a process.
Yeah.
So if I'm root on the kernel of that host,
Right. So.
we see all the memory of the VM, then what do we protect then?
So the point is the kernel needs to be in the TCB as well. Yeah. Right. Yeah. If the kernel is compromised, that you can easily set up some key ID to some other place. You can manipulate the key ID on the page table. So everything breaks, I think. So yeah, for MKTME, kernel has to be in the TCB. Yeah, essentially, basically.
Related question then. What I don't understand is how does KVM in the kernel have access to memory of all guests like it would today?
You mean KVM module can access all the...
Right, so the KVM module running in the kernel,
Yeah.
can it read and write all guest memory in this scheme?
Yeah, sure. If the just like that, if the kernel is compromised, which means you can certainly set up, any key ID in the EPC page table, or you can set up any key ID when you do some key map to access that page with some particular key ID. Yeah.
Couldn't you achieve most of the same security benefits just by unmapping things that aren't in your key space? So like separating out, I don't know, address spaces within the kernel or playing a lot of these games seems like it would get you to the same place.
You mean enhancing the security by isolating? I'm not sure whether I understand your question correctly. I'm sorry.
So like, let's say like instead of using keys, let's say you just didn't map in the memory if the key ID wasn't, like if you weren't supposed to see it. Like it seems like it would get you to the same place. So like within KVM, or I'd say between Qemu processes that should only be able to view a single VM, you just don't map it in. I guess I'm confused by something here. I guess I can talk to you after this.
Oh, okay.
So thank you all for attending, and we are out of time. So thanks.
Okay. Thank you very much. Okay. Thank you very much. Thank you.